So there's going to be three typical rice questions. And it's important, I call them rice because I include the reaction. And it's important that you understand how to do each of them. Okay? This one just has a generic equation. You might say, oh, it doesn't make any sense. What the heck is A2 plus and what the heck is 3B minus? But all they're saying is it doesn't matter what the elements are, or what the compounds are, so long as you have the equation. So this is, for me, what the R part of the rice is. It's the reaction. And if you look at the question, they tell me that they're inserting 3.6 moles of this substance. So that's the initial of that. And 6.8 moles of this substance. And when they tell you something like this, what you assume is that there's no product yet. We're mixing these, they're going to react, and they're going to create product. Essentially, the seesaw of equilibrium is way over here on the reactants, and the only way to balance the seesaw is to create products. To create products from zero, so that's what the initial of the product says, is zero. Typical question where one of the things is zero, is that this must go up. And for this to go up, it must come from the reactants, so these must go down. That's an important step in the rice, is to figure out which one's going up and which one's going down. So since this is zero, we know it's going to go up. In other words, the change is going to be positive. And then we put a division line between the reactants and the products. Since this must go up, these must go down. And we don't know by how much they're going down. We just know that we're going to talk about a certain amount. So we say, well, all the product is getting it is coming from the reactants, so they're going to go up by the same amount that these go down. But this is where the coefficients come in. This one has a coefficient of 3, this one has a coefficient of 1, and this one has a coefficient of 1. That means for every amount this goes down 3 times as much to feed it to make the one product. This goes up by 1. So what we say is this is going down by X amount. This is going down by 3x amount. It's going down by 3 times as much as this amount is. And this one's going up by X amount. So essentially it takes 3 times this amount to make one of these. So then we do the E line. The E line is always this formula. Initial plus change is equal to E. So if I look at this first line, my initial is 3.6. My plus E is my plus change is plus minus X, which becomes a minus. This one is 6.8 plus a minus 3X. Plus a minus 3X, which becomes minus 3X. And this one is 0 plus X, which just is X. Right there, these three quantities are concentrations that these compounds will reach at equilibrium. This is the product side of it. Remember, there's a division line, and this is the initial side. Now, they don't tell us KEQ, but what they do tell us is that the equilibrium of B minus here is 0.4. That means this equation here is also equal to 0.4. So that means we can figure out what X is because we have one missing variable. We'll skip what determined KEQ is. So we're going to focus on what they tell me. They tell me that B minus at equilibrium is 0.4 moles. Well, we also know that while B minus is equal to 0.4, B minus, we can see in that column, is also equal to 6.8 minus 3x. That means since we have two equivalencies, that means that we can replace B minus with 0.4. And it's going to be equal to 6.8 minus 3x. We subtract 6.8 from both sides. We get minus 6.2. It's basic algebra now. Sorry, minus 6.4 is equal to minus 3x. We divide by minus 3 on both sides. The minuses disappear. 3 goes into 6 2 times. It's going to go into 4 once, with a 10 left over, so you get this for X forever. So that means X is equal to this many moles. Now you can take the other two lines, and you instantly, okay, now we can say, well, we're dealing with two significant digits. So it's 2.1. So now we can instantly say, well, that's 2.1. We've already been told that this is 0.4. And we just have to do the last one, 3.6 minus x. X is, we figured out 2.133. So that means this is 1.466666 or 1.5. Now, I think technically these can be determined. Yeah, I think maybe this one can be determined at two significant digits, and these ones can be determined at 3. So it might be possible to replace this at 3.6 minus 2 is 1.466666 or 1.47. So it might be possible to do this. And actually this other one is written as May2. Yeah, I think this one is stuck at 1. So this probably is 1.5. Now we have the three equilibriums here, and we can use our equilibrium equation. KEQ is always equal to the product of the concentrations of the products divided by the product of the concentrations of the reactants. Make sure everything's aqueous or gas. And we have the numbers now. The products is just the concentration of 2.1. And we have to look at their coefficients again. There's only a 1 in front of that product. So it's to the power of 1, or just the concentration. And then we have to look at the reactants. The A has just got a coefficient of 1, so it's 1.5 to the power of 1. And the B minus of 0.4 has a coefficient of 3, so it's a power of 3. So when we do this in our calculator, make sure you put a brackets when you're dividing by treat the denominator as a bracket. So divided by open bracket 1.5 times 0.4 to the power of 3, close brackets, equals. And this is our KEQ, 2.21.875. And we also have to remember that we're to two significant digits, so it's 22. Now, I've double-checked this several times. The book says that the amount at equilibrium of A2 plus is 0.8. That's impossible. I've triple-checked the numbers, so they did an arithmetic issue. And they say the KEQ is 20, which is also impossible because we have two significant digits. So I'm quite sure the book answer is incorrect, but this is how you would do a typical Rice table. I'm 99.9% sure I'm correct because this is the only way you do a Rice table, and this is the only information they've given us. I think they've accidentally put an exponent in the A, forgetting that that's not an exponent or something. They've done something strange, but it's definitely minus 3x when it's 3 times the moles. It's definitely plus 1. It definitely starts at 0. This is a typical Rice table, so I still want you to take this as a typical Rice where they give you the amounts of two of the concentrations and you have to figure it out. Now, typically also in these questions is they'll mix it up. They'll tell you, for instance, the equilibrium amounts, but they won't tell you the initial amount of this one, let's say. Then you have to work backwards and just assume that's I and use the formula I minus X is going to be equal to this. And then you figure out what X is so that you can figure out what I is. Or they might not tell you, they might tell you the equilibrium amount, but not tell you any of the initial amounts or something like that. And you have to do some algebra. Now that's a typical one as well that we're going to do next. So in this one, they don't tell you whether they've injected enough of one gas or another. So what you have to do is construct a Rice table. Again, I prefer Rice. You start with the reaction in line R, and notice they give us the KEQ right away. And they tell us the initial of all 4 gases. Fortunately, it's in 1 liter flask, so this 0.6 moles is also the concentration. So we just consider it big M for each of them. And they tell you it's 0.6 for each. And you might go, well, I don't know which one goes down and which one goes up. Well, you do know what the initial concentration is, and you can construct the KEQ equation based on what you know of products divided by reactants. And the concentrations of these particular products are H2O. Make sure the H2O is gas, because if it's a liquid, you don't include it. And of CO, and it's going to be also divided by the reactants, which is H2 gas, and CO2. Now, fortunately, all of them have the exponent of 1. And what you do here is you see, well, is it at equilibrium now? Is it at equilibrium now when they introduce, and how far off is it? So it's really 0.6 squared divided by 0.6 squared, isn't it? So they made it a really easy one. It's clear that this will come out as 1. Well, 1 is lower than 1.69, and we know where it wants to be is 1.69, which means this has to shift one way or the other. And the question is, which way does it shift? Well, that ultimately comes down to what KEQ is overall. It's products divided by reactants. And for my KEQ to go up, my numerator would have to go up and my denominator would have to go down. For KEQ to go down, my numerator would have to go down and my denominator would have to go up. That's how all fractions work. For a number to go up, the numerator has to go up, in this case, as the denominator goes down. We can see that this 1 has to go up, which means this number has to get bigger. For it to get bigger, the products must get bigger and the reactants must get smaller, which means in my Rice table, I know that my products must get bigger for my KEQ to get bigger. So essentially, when your trial KEQ, which is called a Q, comes out as smaller than your actual KEQ, products must go up. When your trial Q ends up bigger than your actual KEQ, reactants must go up. So I'll say it again. When your trial Q ends up smaller than the actual KEQ, products must go up. Plus sign must be on this side. Minus side must be on this side. When your trial Q is bigger than the actual KEQ, then reactants must go up and products must go down. That's simply because KEQ is products divided by reactants. So now that we know our KEQ must go up from 1 to this, we know to put the plus sign on this. And since the coefficients are all 1, it's just going to be plus 1x and minus 1x. And we have to figure out what it's going to become. So now this is quite easy. This is going to be 0.6 minus x. On the left side, for both of them, that's going to be the concentration. And not quite enough room to write it. And then on the product side, it's going to simply be plus. Like that. There we go. And then when I do the KEQ equation, it's simply going to be this. KEQ is equal to my products divided by my reactants. But they've given me the KEQ is 1.69. All messy here. Notice that this top can be rewritten as just squared. And this bottom can just be rewritten as the same thing squared. And this 1.69 is just 1.69. So we'll just make it a bit bigger just to make it dominant here. Clean it up a bit. Which means if I square root both sides, I get rid of this. And the square root of 1.69 is something like 1.3 square root. Yeah, 1.3. So I get 1.3 is equal to this. Now I just multiply both sides by the denominator. I distribute it through. 1.3 times 0.6 is 3 times 0.6 is 0.78. I get 0.78 minus 1.3x is equal to 0.6 plus x. I get all my x's on the same side by adding 1.3x to both sides. 1x plus 1.3x is 2.3x. And these disappear. Then I have to subtract 0.6 from both sides. And over here I get 0.18. And then I have to divide both sides by 2.3. So x is going to be equal to 0.18 divided by 2.3. Which comes out to 0.782, blah, 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 comes out to this. That means for each of them, remember it's going to be 0.6 minus x on this side, 0.6 minus x on this side. X is not the concentration. And over it's 0.6 plus that, 0.6 plus that. So on the left side, I'm just going to put it in memory here. I'll clear my memory and put it in memory. So on the left side, it's 0.6 minus my memory. So it's going to be this. I'll clean up my equilibrium. So essentially, you just take whatever amount you had, 0.6 minus x, and you're replacing it with what you've discovered your x is. And then you're doing the actual subtraction there. And you're getting this. And then you're going to say, well, we're 3 significant digits. So that means these concentrations on the left are all this. And the other ones are 0.6 plus that, which is a little easier, 0.678, 0.678. And those are the concentrations. And if you want to make sure you got the right concentrations, you do the KEQ formula of it's the concentrations of the products divided by the products of the reactants, and you should come out as 1.69. It's always good if you have time, clear your calculator screen. And make sure. And I get 1.687 or 1.69. So there you go. Those are indeed the final concentrations. And their question is, what is the H2 at equilibrium? It is this. Always answer the question. And don't forget, your units, you'll lose marks. All concentrations are in molarity. So that's the second typical rice, in that they give you the amounts and you're not sure if it's going to go up or down, and you have to compare it to the actual KQ. The third one is tricky. The third one is a good example. This is number 13 on page 184, I think it is. And essentially, several items are mixed and it reaches equilibrium. And then a new item is added, and you have to use the seesaw to determine what would happen. So let's do a typical rice table. And they also want you to graph, so you have to learn how to graph properly as well. Let's do a typical rice table. And they tell me that in a 500 milliliter flask, so half of a liter, that means I have to adjust all these up by doubling them. And they tell me that this is the reaction we're looking at. Now, notice that the product has a 2 in front of it. And they tell me it reaches equilibrium. So it's essentially going to reach equilibrium. And if I divide all of these by 0.5, we get an equilibrium of, it tells me, they're all going to reach an equilibrium of 5M, 5M, and 10M. Well, we have an equilibrium right there. They tell us that reaches equilibrium in a 500 milliliter flask. So we can figure out what is the equilibrium constant at that for that equilibrium. And we know that KEQ is equal to the products. In this case, it's the concentration of HBr squared. Ignore that funny bracket. Times the reactants, and the reactants are all to the power of 1, because there's no coefficient in front of them. We know 5 times 5 is 25. And up top, we're talking about 10 squared. 10 squared is 100. Because they gave us all the concentrations at equilibrium. 100 divided by 25 is 4. So we learn that the KEQ of this is 4. Very useful. Put it aside. Then they tell us something interesting. They tell us, okay, at that point, after equilibrium is reached, we're going to introduce some Br2. Ask yourself, which side of the equation is Br2? It's on this side, and this is where the seesaw is useful. When I add Br2 to what's already equilibrium, it's going to force the seesaw down this side, and nature's going to create more products to balance the seesaw again, which tells me I have these initial amounts because we've already reached equilibrium, and they tell me they've added some more Br2, and they tell me they've added 2.5 moles, not molarity. When I divide that by 0.5, it's 5. They've added 5 moles, which means after it's reached equilibrium, I've then added 5 more moles of Br2 right here. And as we just showed with the seesaw, that's going to tilt the seesaw down, and then we're going to create more products to balance out. Nature is, which means the change for products is going to be plus, and the change for these is going to be minus. Notice that this is new initial when we added the 5, and the 5 is 10. So right away, looking at this table over here, we should write the various amounts. So let's do, before I start fiddling with them, let's do this in red, this in green, and this in, and I'm just actually, instead of writing above it, then do green, and this in blue, and the products in red to really distinguish it. So we can see that it reached an equilibrium at 10 moles. So we're going to find 10 moles here. We're going to draw a line in red to show that flat, to show it reached equilibrium. And it tells us at 35 seconds. So we're going to go all the way to 35 seconds before something happened. Notice that the Br2 was not 10 moles. It was 5 before they added new. So that means down here at 5 until 35 seconds when something happens. And notice that the H2 in blue was also 5. Now at 35 seconds, they introduce 5 more moles of Br2, and that would be shown as a spike upwards. Oh, let me just get that other one color. And Br2 is green. So I would take my line, and at 35 seconds, we would see a spike all the way up here. And then it and the other reactant we've already determined is going to go minus. So that means this reactant is going to slide down to a certain amount. This green reactant is going to slide down to a flat line, but the flat line of this one's going to be higher than that one. And this red product is going to go up and curve like that and reach an amount, hopefully on the chart. We don't know where the numbers are going to be. That's what we have to use the Rice tables for. But we know at 35 seconds that this happens. So that means we have to say, okay, well, if I look at each thing, the E line is going to be 5. What's it going to be? It's going to be 5 minus 1x because there's no coefficient. This one's going to also be minus 1x because there's no coefficient. But this one's going to be plus 2x because there's a coefficient of 2. That means my final equivalent line here is going to be 5 minus x. This one's going to be 10 minus x because we added 5 extra moles. And this is going to be 10 plus 2x. We just need to figure out what it's going to be now. But fortunately, we've already figured out the KEQ. And we know that KEQ is equal to the products, concentrations, divided by the 2 reactants. And we also happen to know that that's going to be equal to 4. Because they told us in the beginning. Well, we know our products is now this. And our reactants is now this. And I'll just keep a copy there. And it's just a matter of figuring out what that is. That's all going to be equal to 4. Okay. Now, in this, they often determine not to use the quadratic. I am going to use the quadratic. Oh, hang on. We're not going to use the quadratic equation because, and they never want you to, by the way, which is a shame. They should let you. Because it says right in there we can solve it without a quadratic. So let's see how we do it. Oh, yes, of course. I forgot one important thing right here. It's a square. It's a square because the product has a coefficient of 2. The reason it can be solved quadratically is because there's going to be cancellations. When I expand the bottom one, 5 times 10 is 50. 5 times minus x is minus 5x. Minus x times 10x is minus 10x for a central thing of minus 15x. And then it's plus 4x squared. Sorry, plus x squared. That's going to be the denominator. To get rid of the denominator, I multiply both sides by that denominator, which means this whole thing on the left, on the right rather, even smaller, is going to be multiplied by 4. That's how we get rid of the denominator. Multiply both sides by it, and it ends up here on the numerator on the right side of the equation. And it's gone here. When I do that, when I multiply the 4 times each item, I get 200 minus 60x plus 4x squared, and that's the secret there. When I expand this one on top, it's that times itself. So it's essentially that times itself. And I FOIL it or distribute it. I get 100 plus 40x. It's plus 20x plus 20x plus 4x squared. That 4x squared on both sides of the equations is what's going to allow me to solve this without the quadratic formula. So this is what I get on the left side. This is going to be equal to that. When I subtract 4x squared from both sides, this ends up canceling. And that's why it's going to work out. When I add 60x to both sides, it goes to this side. So I got 100 plus 40x plus 60x, which is 100x. And it disappears on the left side. Then when I subtract 100 from both sides, I get 100x is equal to 100. And then I get x divided by 100 each side. X is equal to 100 divided by 100. It's 1. Now I can go back to the equilibrium line and say, okay, if x is 1, then 5 minus 1 is 4. This one's going to be 4 moles. And 10 minus 1 is going to be 9. This one's going to be 9 moles. And 10 plus 2x, which is 2, it's going to be 12. And to make sure that you got it right, you then go to the equilibrium line, equilibrium equation, and you do the products, which is going to be squared, divided by the reactants, which is 4 times 9. And 4 times 9 is 36. And 12 squared is 144. And 144 divided by 36 is 4. So since we got the right KQ that we started with, we know that these are indeed in equilibrium, which means we can now chart it, which means that this blue line, which is H2, goes down to 4. And it says in the question that it takes 55 seconds to reach the new equilibrium. So we go to 55 seconds and we find out where 4 is, and we write a blue line, flat line at 55 seconds right there. Make it blue. And we know that the green BR2 is going to spike up to 10, but then go down to 9. So that this green line at 55 seconds is going to be down to 9, which is here. And we know the red line, which was 10 M, going to go up to 12 M, which on the chart at 55 seconds is here. Going to go up to 12. Now it's simply a matter of putting a gentle curve in there, connecting them to show that, oh, sorry, it's going to react the other way, not like that, right? There we go. It's going to react quickly at first and then slow down. And then the green line is going to do like this. Again, it's going to react quickly and then slow down. And the blue line is going to go like this. React quickly and then slow down. This is an important question, especially reading the details to make sure that your flat line occurs at 55 right here, and to make sure your incident occurs at 35 because it's in the question. It's also important to understand how to figure out what goes up and what goes down, and to understand the seesaw, to understand, notice that the equilibrium, the green line, is higher than what it was, even though some of it got consumed. That'll always be the case. Only the blue concentration is lower than where it started. Everything else is higher than where it started. That's because BR2 got added to the system. This is a very important question in that you have to figure out your KEQ to then use it later on. Also keep in mind that they love mixing it up by telling you, for instance, the final amounts, but not telling you maybe how much was added. They'll just say a certain amount of BR2 was added. So you'd have to go 5 plus a certain amount, 5A. And then your equivalent line down here is going to be, equivalency is going to be initial. Equivalency is always going to be equal to initial plus change. And since my initial is 5 plus a mysterious amount, plus my change, which is minus X, it's going to be equal to this. And they're going to tell you, okay, well, the final amount is 9. And you're going to eventually figure out, oh, well, X is 1. And so then you're going to figure out, okay, well, 5 minus 1 is 4. And then getting A all alone, A is equal to 5. So now you figured out the amount they added is 5. They do that all the time. This is a common question as well, where they ask you what the initial amount was added instead. Very important question to master.